Okay guys, this is problem set number 27. It's another molarity problem set, but it's a bit more detailed in terms of the fact that it uses stoichiometry quite a bit more, incorporating the balanced equations that are needed to do some of the calculations here at the bottom. The first four are actually pretty simple, and they're actually very similar to the last problem set, so let's check them out. Number one. What's the molarity of a solution if 25 grams of silver nitrate is diluted to 256 milliliters with water? So we take the 25 grams of silver nitrate, start our problem out with that. And if you remember, molarity is moles per liter. So this 256 milliliters needs to be converted to liters. So we're just going to move that decimal point over 3 times, making that 0.256 liters. So I've got grams per liter, but obviously that's not what I want. I want to get to moles per liter. So I'm just going to multiply by the molar, 1 mole of silver nitrate over the molar mass of silver nitrate. You can see my grams of silver nitrate cancel out with grams of silver nitrate, and I'm left with moles per liter. So if I calculate that out, 25 grams divided by 0.256 divided by 170, I'm going to get 0.57 molar AgNO3. So again, kind of like the last problem set that we did in class. Alright, next one. Kind of the same thing. What's the molarity of a solution if 640 grams of barium hydroxide is diluted to 2.2 liters with water? And so it's the same thing, except this time they give you the liters unit instead of the milliliters unit. I'm going to have you try this one on your own, and I'll tell you the answer is going to come out to 1.7 molar barium hydroxide. So once you give this one a try on your own, just to make sure that you can do it, it's just like the one that you saw up top. Okay. Let's take a look at number 3. How many grams of sodium hydroxide are needed to make 50 milliliters of a 3.5 molar solution of NaOH? So again, this is like problems on the last problem set as well. We'll take a look at how to do that. Start off with what they give you in liters, 0.050 liters. And I'm just going to set my problem up. I know that they want a 3.5 molar solution, so I know I'm going to have 3.5 moles for every 1 liter. And again, we're trying to get to grams here, so it's easy, as you guys know, to go from moles to grams. So I'm going to go, okay, well, for every 1 mole of NaOH I have, I've got 40 grams, and of course I get that molar mass off the periodic table. So check my units, make sure that they cancel out, liters, moles, and grams, it's left. So if I do my calculations, 0.050 liters times 3.5 moles times 40 grams comes out to 7 grams of NaOH. And take a second though and think about what this actually means, right? Because this means that you're going to have to take 7 grams, right? If you have 50 milliliters, you want to make 50 milliliters of a 3.5 molar solution of NaOH. You actually need to go get 7 grams out of the source container. You should have your 50 milliliters of distilled water ready to go. And that 7 grams will probably go right into that 50 milliliters. Alright, the next problem's just the same. And so again, I'm going to give you the answer to that so that you can rock that one out and see if you get the right answer. So here's the answer to this one. 0.69 grams of aluminum phosphate. So give this one a try, set it up, and see that you can come up with the right answer as well. So now with number 5 and 6, 7 and 8, things get a bit more detailed, and nothing that you're unfamiliar with. It's just stoichiometry, and we're going to be using molarity instead. So you've already done the lab and used stoichiometry for a couple of them near the end, where you had to take the molarity of the nitric acid, or you had to take the molarity of the sodium hydroxide. In this case, in these next couple problems, we're actually going to start the stoichiometry off with molarity. So let's take a look at this number 5. In the reaction between 40 milliliters of hydrochloric acid, 0.50 molar hydrochloric acid, and excess zinc, how many grams of hydrogen can be formed? So before I can do anything, of course, I have to write the balanced equation. So I have hydrochloric acid right here, HCl, right? And it's saying excess zinc. This is nice because right away it's telling me excess zinc. I don't have to go find a limiting reactant. I just know it's zinc. This is a single replacement reaction, as you can see. So I'm going to need to write my products. Zinc chloride, and this is going to be hydrogen gas. So I have to balance this because I've got 2 chlorines here and I only have 1 there. So I pop that 2 on right in the front. And now I've got my balanced equation. Let's just see that there. Okay. So we start off by looking at our limiting reactant here. This guy, hydrochloric acid. He's our limiting reactant. And we have 40 milliliters of hydrochloric acid. So I'm just going to put that in liters again. 0.040 liters is what I have of that hydrochloric acid. And I'm going to start my problem off the same way that we did up top. So I have, let's start way over here, 0.040 liters of HCl. And again, we're trying to get to hydrogen. We want to know how many grams of hydrogen, right, can be formed. So I'm going to work my way from hydrochloric acid all the way to hydrogen. So I know I'm going to need a little bit of space here. Using the molarity of the hydrochloric acid, I know for every 1 liter of HCl, I've got 5 moles of HCl. And then looking at my balanced equation, right, I can see that I have 2 moles of HCl for every 1 mole of H2. So I'm just going to use that as my conversion factor right here. 2 moles of HCl, 1 mole of H2. Well, it's asking me for grams of hydrogen, so I'm going to obviously use the molar mass. 1 mole of H2 is 2.02 grams of H2. And of course I'll calculate everything out. 0.040 times 5 times 2.02 divided by 2, and I'm going to get a pretty small number, 0.02 grams of H2. Only got 1 sig fig here. I should probably have 2. Actually, no, just the 1 sig fig with this guy. Correction, by the way. Take a look here. This is 0.5 moles of HCl, not 5 moles of HCl. So 0.5. So 0.040, 0.5. The answer is still the same. I already did my calculations earlier, so my answer is still correct. Let's look at number 6. It's the same problem, same setup. You've got a volume of silver nitrate. Here's the molarity, 0.5 molar. You react it with excess copper, Okay, so it's going to give you, and I'll start off that problem for you, AgNO3. Okay, so this is a solution of silver nitrate plus copper, which is solid, another single replacement reaction. So go ahead and write those products. It should be pretty simple, you can see. Let me give you the answer here. You should be getting 2 grams of silver for your answer. So give this one a try and see if you come up with the right answer. Again, you're going from the silver nitrate to one of your products, the silver. It says how many grams of silver can be prepared. Of course, you need to figure out what the other product is going to be, and that should be pretty simple for you. Number 7 is kind of beastly, and actually I should have given you guys a little bit more room to do it, but we'll squeeze it in here. Maybe I'll go on the back actually and do it. Let me give you another piece of paper here. I'll start by writing out the balanced equation. There's quite a bit going on here, but don't let it confuse you. Okay, let's just take it step by step. In the reaction between, there's 40 milliliters of 6 molar HCl. Okay, so I know I've got HCl as one of my reactants, so I'm just going to write that right here, HCl. I'll come back to the fact that there's 40 milliliters and there's 6 molar. We'll get to that eventually. And 50 milliliters of 2.5 molar barium hydroxide. Okay, I've got some barium hydroxide, so I'm just going to jot that down. How many grams of barium chloride will be formed? Alright, well I've got some barium chloride forming, so I know how to write the formula for that, as well as you do. Just going to make sure that I continue on with the rest of my products. So if I have HCl and barium hydroxide, it's a double replacement reaction. The barium and the chlorine came and bonded together, which means the hydrogen and the OHs are going to bond together as well. So we're going to get some water out of this. So H2O. Got to make sure everything's balanced. So if I check, I'm going to need, because if you look over here, I've got my 2 OHs. So again, I need to have 2 OHs over here. I'm going to put a 2 in front of this guy. If you wrote HOH instead of H2O, a little bit more obvious. So 2 OHs, 2 OHs, and of course that leaves me with 2 more H's I need on this side. So I'm going to put a 2 right here, which is nice because it balances out those chlorines right here. 2 chlorines, so we're all set. So with this problem, this is actually a limiting reactant problem. And instead of grams of our reactants, we've got volumes and molarities. Okay? So we're going to have to do figure out what our limiting reactant is right now. Alright? So first we'll take and get more space here for you. A little bit more paper here. Okay. And what we'll do is we'll go from, well, we could do it either way. We'll go from liters of barium hydroxide to grams of barium hydroxide. So let's start by doing that.